Welcome DEKWP, 小工 Abor. Your learning journey starts now. Ever felt like some mathematical proofs are just black magic? You follow the steps, they check out, but the insight? Missing. What if the real story isn't just the logic, but the meaning behind it? So, traditionally, math is built on axioms. Solid ground, right? We define our terms, lay down the rules, and then it's all about logical deduction. Modus ponens, modus tollens, the whole shebang. It's rigorous, it's consistent, it's, well, sometimes it feels like describing an elephant by only touching its tail. You get the shape, but not the majestic beast. This purely formal approach, while powerful, often misses the why. It explains how we know something, but not necessarily why it feels important or where it fits in the grand scheme. That's where the fun begins. Enter the DIKWP model. Think of it as layers of understanding. At the bottom, D for data, just the raw stuff, symbols, numbers, examples. For Fermat's last theorem, it's x to the power of n plus y to the power of n equals z to the power of n. Then I, information. We start seeing patterns, differences. Hey, n equals 2 works, but n greater than 2 seems impossible? That's information. Next, K, knowledge. This gets structured into theorems, theories, the vast web of established math. Above that, W, wisdom. This is the clever part. The proof techniques, the strategies, the actual act of proving. Finally, P, purpose, the big why. Why are we even asking? Fermat's challenge? Unifying prime distribution. This is the driving force. These layers aren't separate, they constantly interact. Now, here's the kicker, semantic tension. It's the friction between these layers. Maybe your grand idea, your purpose P, clashes with what we currently know, knowledge K. Or maybe you spot a weird pattern in your data D that doesn't fit the existing knowledge K. This tension, this cognitive dissonance, is the engine of discovery. It forces us to leap. We might try to compress our high-level intent P directly into a precise conjecture, creating huge tension if the knowledge base isn't ready. Or, when stuck, we bounce between our knowledge toolkit K and our ultimate goal P, trying different proof strategies W. Sometimes, we need to go back to the data or information layer to find new clues. Resolving this tension, finding that elegant proof that connects everything back neatly, that's when semantic closure happens. The system stabilizes. And this leads beautifully into the bug theory perspective. Think of those famous unsolved problems, Riemann hypothesis, twin primes, not as failures, but as bugs in the mathematical universe. Imperfections, gaps in our knowledge network. And according to this view, these bugs aren't bad things. They're precisely what drives progress. They create tension, forcing us to develop new tools, new ideas, higher level thinking. It's a cycle. Discover a bug, keep the tension simmering, eventually fix the bug with a proof, and then, surprise. Often, fixing one bug reveals another, deeper one. It's like peeling an onion or climbing a mountain. Every peak you reach reveals a new horizon. This bug awareness is crucial for mathematicians. So, why are some problems so darn hard? Look at FLT again. Its statement is incredibly simple, highly compressed. But it touches upon so many disparate areas of math, number theory, algebraic geometry, modular forms. This extreme compression combined with a massive cross-domain requirement creates immense semantic tension. Proving it required expanding the entire knowledge landscape. We propose thinking about probability not just in terms of logical steps, but using metrics like semantic complexity, how deep the concepts are, how interconnected they need to be, and tension compression, how much information is packed into that little statement. This gives us a richer way to understand difficulty beyond just counting symbols. What does this all mean? Huge implications. For AI, current systems are great at following logic, but they lack true mathematical intuition. A semantic framework could give them a roadmap, helping them understand why a problem is hard, guiding their search for proofs. Imagine AI assistants that don't just calculate, but reason about meaning. Philosophically, it bridges gaps, acknowledging objective mathematical structures while recognizing the human cognitive process in building them. It even gives us a handle on mathematical beauty, the satisfaction of resolving semantic tension elegantly. The future, likely a partnership. Humans bring the big picture vision, the sense of purpose, and semantic navigation. AI brings brute force calculation and logical verification. Together, tackling the next generation of mathematical mysteries. That's the semantic turn.